Hello, I'm Dr. Steve Cheney, and tonight I'm going to talk about the truth about methyl folate. But first, let me introduce myself. I'm a teacher. I taught biochemistry and nutrition to medical and dental students at the University of North Carolina for 40 years. I'm also a research scientist. I've published over 100 papers in peer-reviewed scientific journals. And I'm speaking to you tonight really as editor-in-chief of Health Tips from the Professor, a weekly blog where I take on the hype, the myths, the lies that you hear so frequently in the internet about nutrition and supplementation and which foods you should eat. And I go to the studies behind those headlines, I analyze the science, and I give you the truth. So let's talk about urban nutrition myths. Now, I think everybody knows what an urban myth is. That is a myth that's been repeated over and over so many times that people kind of believe it's true, but it really isn't. And there are a lot of them in the nutrition realm that are really of the same type. They often start with a blog or a website, and the message is based on the bias of the particular author who wrote it. And they'll sometimes confuse animal studies with clinical studies. And even when they do choose clinical studies to report on, they choose them selectively to support their bias. They kind of cherry pick the studies that support what they believe in and ignore the studies that say something differently. And, their message is always spectacular. They never let the facts get in the way of a good story. Some of those websites are unfortunately authored by doctors, but they have their biases too, and many of them write these websites every single week, sometimes more than weekly. Sometimes they have TV shows and they have the same sort of pressure because every week they've got to come up with something new, something exciting, something spectacular, and there's just not that much spectacular information out there. So if the headlines are always about miracle foods or nutrients that are going to prevent disease X, or foods or supplements that might just kill you, and by the way, the establishment isn't telling you about it, they can't all be true. Now, I do want to acknowledge that some of those doctors are well-meaning, and my message to them is that I promise not to practice medicine if they would promise not to try and practice biochemistry, because they're not trained scientists. They rely on observations, case studies, they misinterpret the scientific literature, and then there's the media. And the media has their biases. They aren't trained in how to interpret scientific studies, but remember, it's a spectacular, the man bites dog story that sells subscriptions. I love this picture I found on the internet. It really speaks to so much of what we, hear nowadays in the media that isn't a reflection of reality. And once that story's been repeated often enough, it becomes generally accepted as true, it becomes another urban myth. So I'm going to tell you to question what you've been told, or perhaps rethink what you believe. So I'm going to talk about the mythology of methyl folate, because there are a lot of urban nutrition myths about methyl folate, but one of the things, this is a complicated subject. It does require some biochemistry. It does require talking about metabolic pathways. And I know that some of you who are going to be listening and watching this video are well trained, and you have seen, you've read some of the things that are out there. They often go into a great deal of detail, so I feel an obligation not to take this too lightly. But what I will tell you, for those of you who aren't biochemists, you don't want to know all this information, I'm going to do what any good teacher does. I'm going to tell you what I'm going to tell you, and then I will tell it to you. And at the end, I'm going to tell you what I've told you. So most of you heard about the methyl folate. Most of what you've heard about methyl folate is a myth. It's not a fact, not reality. Folic acid and methyl folate have exactly the same effects in the body. Folic acid is actually much better research than methyl folate. We know that folic acid is effective. We know it's safe. We think that methyl folate is probably just as safe and just as effective, but there's much less evidence to support it. And here is the biggest myth of all. Folic acid works just as well as methyl folate even in people that have something called a methylene tetrahydrofolate reductase deficiency. And I know that's a mouthful, but that's the enzyme that makes methylfolate in the body. So there's been a lot of hype around that, people with that particular deficiency, and there's a lot of myths that they have to use methylfolate. Of course, the other thing is folic acid is usually less expensive than methylfolate. So if methylfolate doesn't really work any better, folic acid is much better researched, folic acid and methylfolate have the same effects in the body, why would you buy something that's more expensive? Now, what I'm going to do next is I'm going to go through the 6 common myths about methylfolate, and I'll tell you which of those are false, which of them are maybe partially true under some circumstances, and I'm going to sprinkle some biochemistry in there. So if you get confused with the biochemistry, the metabolic pathways, just focus on the 6 myths and whether they're true or not true. So let's start with a little bit of biochemistry and ask, what is folic acid? So if you look at the structure at the top, it's kind of a complicated structure, and I'm not going to go into the chemistry of it. That's folic acid. And if we reduce it, we add those 2 little red hydrogen there, we get dihydrofolic acid. And if we reduce it one step further, we add 2 more hydrogens, we get tetrahydrofolic acid. Now, tetrahydrofolic acid is the most reduced form. It's also the least stable form. Folic acid is the most oxidized form. It's the most stable form. And it's the most stable form because we live in an atmosphere of oxygen. So everything tends to get oxidized. It's very difficult to keep things in their fully reduced form. So the oxidized form is the most stable. That's folic acid. Now, there is sort of a complicated terminology here, and that is traditionally we've called all 3 of these, folic acid, dihydrofolate, and tetrahydrofolic acid, as folates. But nowadays, and so that's a terminology you'll see quite frequently, but nowadays we've kind of looked at just calling tetrahydrofolic acid as folate, and the other 2, either folic acid and dihydrofolic acid. So I'm going to mostly use the new terminology. When I refer to folate, I'm going to be referring to tetrahydrofolic acid. But if you've heard it, you've heard previously, sometimes folic acid is referred to as a kind of folate. It's just a confusion in the terminology. Now, tetrahydrofolic acid is the form in which folic acid exists in the cell in its most reduced form, and it plays a very important metabolic role. It carries 1 carbon units, which are building blocks for metabolism, so it plays a very important metabolic role. Now, one of those 1 carbon derivatives of tetrahydrofolic acid is N5-methyl tetrahydrofolate, and that's the one that we typically refer to as methylfolate. So I will show you the N5-methyl tetrahydrofolate, but I'm going to be calling this methylfolate throughout because that's what you hear it as. So let's summarize what I've just told you. Folic acid is the most oxidized and stable form of folate. It's easily reduced to tetrahydrofolate, for which the common name nowadays is folate in the cell. Folic acid has been used as a supplement since 1945, and it's supported by over 40,000 studies. So we know what it does, and we know how it works. Folate, which is a common term now for tetrahydrofolate, or THF, is a carrier of 1 carbon units, those metabolic building blocks I was talking about. It's the most reduced and unstable form of folate. It's also the biologically active form of folate that we find in cells. And methylfolate is just one of several derivatives of tetrahydrofolate that's found in the cells. So that brings me to myth number 1. Methylfolate is natural and folic acid is not. I'm sure many of you have heard that from your doctor, maybe your friends. You've read it on the blogs and websites. So let's examine that myth. It actually is completely false. if you look at the patents for preparation of N5-methyl tetrahydrofolate, which remember is the chemical name for methyl folate, those patents are held by Merck and Pamlab, the nutraceutical division of Nestle, and if you look them up, which I did, the synthesis starts from folic acid. So methyl folate can never be more natural than folic acid. And even then, it's a purely chemical synthesis. Methyl folate is not something prepared from biological materials. And I know you will find some manufacturers who will claim that their methyl folate just comes from foods. Well, let's look at the truth or potential of that. And that if we just look at the food sources that it would be required to make a single 400 IU tablet of methyl folate, or any kind of folate for that term. Now again, we're using here the reduced form, the tetrahydrofolate. So this is the active form in the cell. If we just wanted to make a 400 IU tablet of folate, that would require 1 cup of lentils, 2 cups of cooked spinach, 4 cups of broccoli, 4 papayas, or 10 cups of almonds. Let's wrap our minds around that for just a minute. Let's say you converted that entire cup of lentils into a powder. It's really pretty unlikely that you're going to be able to have a small enough amount of powder to get all of that into one 400 IU tablet of folate. Same sort of thing with 2 cups of cooked spinach and all the others. And, you know, that's just the beginning, because that's assuming you had 100% efficiency of extraction. You're never going to get to 100% efficiency of extraction. And by the way, we're looking at all forms of folate here. Not all of the folate in that lentils and that spinach is methyl folate. So, you know, if you're getting your supplement from a company that tells you their methyl folate is prepared from whole foods, they're going to lie to you about other things as well. And I guess the other thing to think about that. So we got 2 cups of spinach, 1 cup of lentils. That's to make a single tablet. Do you really think if you've got a bottle with 30 tablets, that's a month's supply of your methyl folate, that they're going to have used 30 cups of lentils or 60 cups of spinach to make it? Not on your life. So let's now get back to a little bit of biochemistry 101, I'll call it. What does folic acid actually do? So here's a metabolic pathway, and to kind of keep everybody from freaking out, I'm going to break it down for you a little bit. So folic acid, I said, is the most oxidized form. That's a form we commonly find in supplements. When that enters the cell, it's reduced first to dihydrofolate and then to tetrahydrofolate. And that tetrahydrofolate, for which the common term is folate now, that enters that is the active compound in the cell that carries 1 carbon units for biosynthetic. So this is sort of a depiction of that. A, B, and C are different 1 carbon derivatives of tetrahydrofolate. And I call them A, B, and C because each of these structures are complicated structures, and each of these names are complicated names. So we really, if I started to go into all the names and structures, people's eyeballs would glaze over. So these are just the 1 carbon derivatives of tetrahydrofolate that you find in the cell. And these are metabolic building blocks for a lot of compounds, but among them several amino acids and the precursors needed for DNA synthesis. And of course, if you think about DNA synthesis, that's going to be required for cell division. So that's sort of breaking this pathway down and making it simple. Now, I haven't talked about methyl folate yet, so let me add that into the pathway. So that's simply, as I said, another 1 carbon derivative of tetrahydrofolate, but it is involved in a very unique reaction. This is a B12 dependent reaction, so it requires vitamin B12 as well as the methyl folate, and it takes a toxic amino acid byproduct called homocysteine and converts it to the essential amino acid methionine. So it's detoxifying the cell by getting rid of homocysteine and converting it to an essential amino acid. And once that reaction is completed, you have tetrahydrofolate, and it just goes back and picks up other 1 carbon units, and the whole biosynthetic process continues. So that's folate metabolism in a nutshell. And the only final thing to mention, that methylene tetrahydrofolate reductase that I talked about, this is the one that you hear so much about. There's so many myths about this in terms of methylfolate. That's the enzyme that catalyzes this reaction. It's the enzyme that's responsible for synthesizing that methylfolate. So that brings me to myth number 2, that folic acid isn't found in nature. Well, it's actually partly true, and that's partly true in the sense that you find very little of it in the cell, you find very little of it in the bloodstream, but it's totally irrelevant. And that's because folic acid is so important that our bodies scavenge every bit of it as soon as we make it. Unless we overwhelm the capacity of our cells to take that folic acid and convert it to tetrahydrofolate, our cells are just going to take the folic acid as soon as it's formed and convert it to the biologically active form, so nothing is wasted. So let me take you through another sort of view of this metabolic pathway. See what happens when you make one of those precursors for DNA synthesis. You actually oxidize the tetrahydrofolate to dihydrofolate, and some of that's non-enzymatically oxidized to folic acid, because remember, we live in an atmosphere of oxygen. So you're constantly producing dihydrofolate and folic acid in the cell. We're producing them all the time. And because of that, we have an enzyme called dihydrofolate reductase that immediately converts them back to tetrahydrofolate so the whole one-carbon metabolism pathway can continue. That enzyme's very efficient. As long as we don't overwhelm the system, it's going to take every drop of folic acid that's formed and immediately convert it back to tetrahydrofolate. And that's why you don't find much folic acid in the cell, because it's all been converted back to tetrahydrofolate as soon as it's formed. That's what that enzyme exists for. So that brings us to myth number 3. I'm sure you've heard this one before, and that's methylfolate is better utilized than folic acid. So let's actually look at that. That's another one that's completely false. If you look at the Institute of Medicine, that's the agency that sets the daily value standards, or RDA standards. They tell us that folic acid is more bioavailable than folates in food. So based on the amount of cellular folates, tetrahydrofolate, folic acid delivers twice as much folate as the folate that you get from food sources. And that's because that folate has been further modified. It's also in a matrix with fiber and other food components. So we don't utilize all of that. Folic acid is much more efficiently utilized than the folates we get from food. But if we look at other studies, in terms of bioavailability of folic acid, it's 90 to 95%. You're not going to get much better than 90 to 95%. And if you look at that synthetic methylfolate, the kind that you're going to find in every supplement that you buy that says methylfolate, its bioavailability is exactly the same as folic acid. That's based on 2 major clinical studies. One of them looked at total distribution, total body distribution. So what that means is you look at all of the stuff that goes into the body, and you look at how much is peed out and pooped out, and you just look at how much remains in the body. And it doesn't matter whether you start with methylfolate or folic acid, you retain exactly the same amount. But another way of looking at it is to look at the amount of folate that's in the cells. And this was a cell, and if you're going to look at cells, it's a little bit difficult to get liver cells or muscle cells. That's a bit invasive. So you take blood. You look at either red blood cells or white blood cells, and when you look at red blood cell folate, the bioavailability of methylfolate and folic acid are identical. So why do some doctors say that methylfolate is better? Well, that's because of a misinterpretation of a single study. This is a study that measured blood levels of folate. Remember, that's the common term for the most reduced form, the tetrahydrofolate. after taking either folic acid or methylfolate. So the green is going to be people who took the methylfolate pill. That's a 400 IU pill. The blue is people who are going to take a 400 IU pill of folic acid. So if you look at blood folate levels, this is what you see. But if you look at blood folic acid levels, this is what you see. So what happens is the people that are telling you that the methylfolate is better utilized are looking at the graph on the left. You can see the methylfolate gets into the bloodstream a little bit faster, and then it, of course, goes into the cell, so it goes back down. And in terms of folate levels, it's going to take a little bit longer for folic acid to start producing folate and get into the bloodstream. So we're looking at that difference, which, by the way, is 20 to 30%. It's not huge, but remember, that's in the blood. They're looking at blood levels, and it's what's in the cell that's the important parameter. But the interesting thing is they totally ignored this part of the study, and that actually is the most important part of the experiment. So let me break it down for you. Let me kind of walk you through this experiment. So subjects took a methylfolate supplement. That methylfolate goes into the bloodstream very rapidly, and then it's taken up into the cells. So that's what you see here. And then you actually see some folic acid escaping from the cell and going into the bloodstream. So what's going on here? Well, in this case, you're getting methylfolate that's going into the cell, and you're saturating all of the tetrahydrofolate derivatives in the cell. And by the way, this was a bolus, a single 400 IU tablet of methylfolate, so you're overwhelming the system. And now you've overwhelmed the ability of that enzyme, that dihydrofolate reductase, to reduce all that folic acid to tetrahydrofolate, and you actually start to see folic acid escaping into the bloodstream. If we were getting our folate from foods, that wouldn't happen, because the folates are more poorly absorbed, they're more slowly absorbed, and they get into the bloodstream more slowly, so you never overwhelm the cells. But when you take a synthetic methylfolate pill, you overwhelm the cells, and now you do see that folic acid escaping into the bloodstream, which this experiment alone proves that folic acid is found in nature. But if we look at the folic acid supplementation, that's even more interesting. In this case, the folic acid goes into the bloodstream and then is taken up into the cells, and a little while later you start to get folate escaping from the cells and going into the bloodstream. So what's happening here? Well, this is sort of the reverse reaction. Folic acid's going in, all this metabolites are getting saturated, and so some of that is going to go back out into the bloodstream as various forms of folate. Now, the interesting thing is that this occurs, the pattern was identical in individuals who were just had normal folate metabolism and individuals who were defective for that methylene tetrahydrofolate reductase gene, and they had the most severe defect in that gene, you were still getting methylfolate formed. So, if you look at the myth, it is truly a myth. Folic acid and methylfolate are utilized equally well. So let's kind of come back before we get to the next myth. I'm going to talk a little bit about the symptoms of folate deficiency. Let's understand that a little bit. So anemia is the hallmark system. This is something that develops relatively quickly. It develops in a high percentage of cases. It's easy to detect. That's the symptom that most often brings the patient into a doctor's office. Now, the other sort of major symptoms that you'll see are elevated homocysteine levels. Remember, that's that toxic amino acid byproduct. And you also see birth defects. And both of these are directly related to cellular folate deficiency. These are easy to quantify, and the relationship between them and cellular folate deficiency has been validated by multiple clinical studies. So this is, we're pretty sure about these being related to cellular folate deficiency. Cancer and cognitive decline are highly associated with cellular folate deficiency, but here the causation is difficult to prove because the disease onset takes decades. And then we get heart disease, depression, mood and learning disorders. These are weakly associated with cellular folate deficiency. And causation is difficult to prove because of genetic complexity. And I'm going to come back to that at the end of this talk. And the placebo effect. And, when you're talking about things like depression, mood, and those sorts of things, the placebo effect is right at 50 or 60%. You give people a placebo, 50%, you tell them they're going to be less depressed or they're going to be in a better mood, 50 or 60% of them will, experience that. So again, the placebo effect makes it very, very difficult if you do a double-blind placebo-controlled study to prove that depression, mood, and learning disorders are really associated with a cellular folate deficiency. So now we're ready to talk about the central myth that is really I think the hallmark of the discussion, and that's if you have a mutation in this methylene tetrahydrofolate reductase gene, the one that makes methylfolate, folic acid isn't going to be effective for you. So let's kind of go back to this pathway again and ask, where do these symptoms occur? So if you have a block in cell division, it's pretty clear that that's what leads to the anemia. That's probably what leads to the cancer. On the other hand, it's down in this bottom part of the pathway where you get the other symptoms. And this is where you get the birth defects, cognitive decline, depression, mood and learning disorders. And there's a bit of a debate in terms of what's the cause of these symptoms. Is it the buildup of homocysteine, because that's toxic to the cell, it causes inflammation, it could cause a lot of these problems, or there are some metabolites. If you block this reaction, you're going to build up homocysteine, but you're going to make less methionine. And there are a number of compounds downstream of that methionine, like S-adenosyl methionine, choline, and betaine. And so if you deplete those could also be related to these things like birth defects, cognitive decline, depression, mood and learning disorders. And the debate is really which one of this is the homocysteine, or is it these downstream metabolites that are causing these defects? Now, my money is with the homocysteine, and that's because whenever you eat dietary protein, you're going to get a source of methionine that's going to replenish that methionine pool. And so I'm not so sure that you're going to have a major defect or a major decrease in the downstream metabolites. But, that's perhaps getting a little bit too sciencey for most people. But anyway, just wanted to bring that in. So let's put this in perspective. Anemia and cancer are, they're in the upper part of that pathway. They're unaffected by methylene tetrahydrofolate reductase deficiency. Everybody agrees that either methylfolate or folic acid work equally well to prevent those kinds of deficiency symptoms. This is the part where the argument comes in. Elevated homocysteine, birth defects, cognitive decline, depression, mood and learning disorders, because they are sort of in the downstream part of that pathway, they could be affected theoretically by methylene tetrahydrofolate reductase deficiency. So for them, the debate is whether methylfolate works better than folic acid to prevent those kinds of deficiency symptoms. And I'm going to go through the logic that proponents use to support their argument. So if you think about, that's where the defect is, the methylene tetrahydrofolate. If you give somebody, so then if you do that, you're going to build up homocysteine. You're not going to have enough methionine. It's this part of the pathway that you're blocking. So if you give somebody methylfolate, now you're replenishing the methylfolate. You can carry out this B12-dependent reaction. You'll deplete homocysteine. You'll replenish methionine. And by the way, that methylfolate is converted to tetrahydrofolate in the process, and you can now take care of everything else in the pathway. Now, if you give somebody folic acid, they can take care of all of those, but the hypothesis is that folic acid isn't going to be able to get past that methylene tetrahydrofolate block and take care of all the other symptoms that are associated with this part of the pathway. So that's a hypothesis. But sometimes there's more than meets the eye. So what you need to know, and you might wonder why I'm starting this part with a picture of a satellite. And that's not just any satellite. That's the Hubble Space Telescope. And I'm using that as a metaphor or an illustration of what I'm going to tell you. Because, I have tremendous admiration for NASA scientists. When they put these things like Hubble telescopes or manned flights into orbit, they built in a tremendous amount of redundancy. So if one system failed, the whole system didn't fail. And the Hubble Space Telescope was a perfect example. You may remember that they had 4 gyroscopes in that telescope to keep it pointed in the right direction so it could take pictures of the heavens. And eventually one of those gyroscopes failed. No problem, they had 3 gyroscopes left. And then a second one failed. They were down to 2 gyroscopes now. Still, no problem, they built in redundancy. Then that one failed, so they were down to 1 gyroscope. And, it wasn't perfect, but the Hubble Space Telescope was still working pretty darn well. And it wasn't until that 4th gyroscope started to fail that they had to send the space shuttle up there to replace the gyroscopes. So that's redundancy. But what you need to know is our bodies were designed by somebody that's much smarter than the NASA scientists. We have a tremendous amount of redundancy built into our systems as well. So what you need to know is most enzymes have excess capacity to carry out their function. 50% activity is usually fine. That's like having 2 gyroscopes left in the Hubble Space Telescope, no problems. Even when enzyme activity is limited to 30 to 40% range, the reaction can still be driven if you have high enough substrate concentrations. In this case, the substrate would be folic acid. If you have high enough folic acid, you can drive that reaction even when enzyme activity is limited. So you would anticipate that higher than normal folic acid levels could overcome a partial methylene tetrahydrofolate reductase deficiency, even in the 30 to 40% range. And this isn't going to take tons of folic acid. We're talking about 600 or 800 international units of folic acid rather than the normal RDA of 400. So put another way, you can think of a partial methylene tetrahydrofolate deficiency as simply increasing the dietary requirement for folic acid. Most enzymes are only truly dead when their activity is less than 10%. So with that kind of perspective, let's look at the mutations that you find in methylene tetrahydrofolate reductase. And there are a number of mutations you find, but there are only 2 that are known to affect activity. So one of those is C67T, 677T. So basically what that means is you change the cytosine to a thymine in position 677 of the gene. And if you look at people who are homozygous for that deficiency, they have 2 copies of the bad gene. They've got 30% enzyme activity. So now you're in that 30% range, where you, things are going to be working pretty well. You can probably drive the reaction with excess folic acid. Now the prevalence of this is about 10% in U.S. population. It's often associated with homocysteine levels. And it can be associated with depression, anxiety, and mood swings in some people. So under certain genetic conditions, you get that kind of association, but it doesn't happen for everybody with that deficiency. And I'll talk more about that at the end. Heterozygotes, they only have 1 copy of the bad gene. They've got 65% activity. They are completely normal in clinical studies, and you would expect they're over 50% activity. They're not going to have any difference. We have that kind of redundancy built in. The other mutation is an A1298C. So it's a adenosine to cytosine mutation in position 1298 of the gene. In this case, homozygotes have 60% activity. That occurs in about 5% of the population, but as you might expect, with 60% enzyme activity, they're completely normal in clinical studies. So let's go to the evidence. What is the evidence that folic acid can replace methylfolate in people with methylene tetrahydrofolate reductase deficiency. And I've given you the references down here, but let me take you through this. It turns out that folic acid is just as effective at methylfolate at decreasing homocysteine levels. And remember, that's one of the sort of direct defects that occurs that's downstream of the methylene tetrahydrofolate reductase gene. And that's true even in people who are homozygous for the most serious form of the gene defect, the one with the lowest activity. Folic acid is effective in preventing neural tube defects, and neural tube defects are highly associated with, again, with that most serious form of the methylene tetrahydrofolate reductase deficiency. And there are studies that suggest that folic acid, B12, and B6 can prevent cognitive decline in older people with elevated homocysteine levels. And remember, homocysteine is highly associated with that methylene tetrahydrofolate reductase gene defect. I say suggest because there's some, there are some variations in these studies. And it's interesting. The one study that was done with methylfolate showed no effect, but that was just one study. I think we need to do more. But, all the studies we have tell us that methylfolate can replace, this folic acid can replace methylfolate even in people with the most severe form of methylene tetrahydrofolate reductase deficiency. So that brings us to myth number 5. And, so people say, okay, yeah, you can give some people excess folic acid. You can overcome that methylene tetrahydrofolate reductase deficiency, but you don't want to do that because it's going to cause cancer. So let's look at that myth. Where did the myth come from? Well, there's a single study back in 2007 that suggested that 400 international units of folic acid increased the risk of colon adenomas in people who are over 50. Now, mind you, adenomas are benign tumors. They're not colon cancer. They can go on to become colon cancer in some people, but that doesn't happen in everybody. So just because you have an adenoma doesn't mean you're fated to have colon cancer. But immediately the headlines started to say folic acid causes colon cancer in people over 50. That's not at all what the study said, but that's what the headlines said. That's where the myth arose. And pretty soon experts were recommending that people over 50 should take a multivitamin every other day because, heaven forbid, you wouldn't want to get the RDA level of folic acid. Now, there was a second study in 2009 that looked at the effect of 1,000 IU of folic acid in colon adenomas in people over 50. And that study showed no increase in adenomas. There was no effect in folates on adenomas overall or in people with adequate blood folate level to begin with. But if you had low blood folate at the beginning of the study, so you were deficient in folic acid at the beginning of the study, folic acid reduced your adenomas by 40%. And by the way, 55% of those participants had low blood folate levels. So this study said exactly the opposite of the first study, but it was ignored. The myth had already been established. And then there was a third study that showed that 800 IU of folic acid didn't increase the risk of colon cancer. So now they've gone beyond this. They're no longer looking at adenomas. They're looking at colon cancer. But this was, again, it was completely ignored because the urban myth had already been established. And finally, the American Cancer Society decided to do the definitive study, published in Gastroenterology in 2011, where they measured folates from food and folic acid from supplements. They looked at almost 100,000 men and women aged 50 to 74. They followed them for 8 years, and they measured the incidence of colon cancer. So the direct thing that you want to measure. And what they found is high intakes of neither folic acid or folates from food, or both, increase the risk of colon cancer. In fact, the people that had the highest intake of total folates from both food and supplements had a significantly decreased risk of colon cancer. So again, just the opposite of what the myth was telling people. But that's the myth that was believed. So what about other cancers? There are some very, again, small studies, a couple of small studies that suggested that folic acid supplementation might increase the risk of prostate cancer and breast cancer. and they're small individual studies, but they've been widely hyped by the methyl folate advocates. But once again, the definitive study has been done. This was a meta-analysis of every placebo-controlled study published prior to 2010 that looked at the effect of folic acid supplementation in cancer risk. This is 13 studies with over 50,000 subjects, and what they found is that folic acid supplementation caused no increase in overall cancer risk, no increase in colon cancer, prostate cancer, breast cancer, or any other individual cancer. And by the way, the average dose of folic acid in those studies was 2 milligrams per day, 5 times the RDA. So again, that myth is completely false. Folic acid is safe and effective, and even effective in people with a methylene tetrahydrofolate reductase deficiency. It finally brings us to myth number 6. Folic acid can mask B12 deficiency and methylfolate does not. Now, it is the anemia in B12 deficiency that brings people into the doctor's office, and it's true that folic acid can mask that B12 deficient, can mask that anemia. And what happens is that, eventually people with B12 deficiency are going to develop cognitive decline, they're going to develop dementia. So you don't want to mask the deficiency. And so this myth is actually true. Methylfolate won't mask the deficiency, but it should be irrelevant because you shouldn't just be taking a folic acid supplement. You should always balance folic acid with vitamin B12. And actually, really, particularly if you're taking a high-dose supplement, it's folic acid, B12, and B6 together that act to reduce the homocysteine levels. So you should really be taking all of those three together. Now, if you're looking for a B complex, now you've got B6, and it works along with thiamine and riboflavin and niacin. So you're looking for a balance of all of the Bs. So why are some doctors so convinced that methylfolate is essential for people with methylene tetrahydrofolate reductase deficiency? That's because they don't understand the concept of genetic penetrance. Now that's, again, one of those $10 words. It's a favorite term of medical geneticists, but basically what that means is the same gene defect, in this case the methylene tetrahydrofolate reductase deficiency, has different severity in different individuals depending on their genetic background. So if, for example, you had the severest form of methylene tetrahydrofolate reductase deficiency in a patient who also had a genetic background that predisposed them to depression, they might have depression symptoms and they might actually benefit from methylfolate. But for 95% of the other patients with that same deficiency, there would be no increased risk of depression. So that's the genetic penetrance. It depends on the background of the other genes that are unique to that individual. But doctors base their conclusions on individual patients. So they have a patient, one patient for which methylfolate works better than folic acid. They look at that patient, they say, oh, well, they do the test, they say, oh, you're deficient in the methylene tetrahydrofolate reductase deficiency. So that must explain why methylfolate worked better for you. And they jump to the conclusion that everybody with that deficiency is going to benefit from methylfolate. So they start giving all their patients with that deficiency methylfolate. And yes, they all respond, but they've never done the double-blind placebo-controlled clinical studies. When you do those, you don't see a difference between folic acid and methylfolate. And that's because, yes, there's some patients who are going to benefit from that, but there may be 1% of the population or 0.1% of the population. That's not large enough to show up in double-blind placebo-controlled clinical studies. And so the other thing is, their efficacy of treatment is enhanced by what I call the white coat placebo effect. I already talked about the magnitude of the placebo effect, but heck, if your doctor gives you a placebo and tells you you're going to get better, that white coat counts for a lot. And they publish their case reports, and then yet another urban nutrition myth is born. But I don't want to give you the wrong idea here, that scientists are always right. We base our advice on double-blind, placebo-controlled clinical studies. Those studies measure the average effect. They tell us what works for most people. They don't tell us what works for you. You could be that 1% or that 0.1% of the population for whom methylfolate is more effective. I've been talking with people. I've had some people tell me that they used to use folic acid. Now they use methylfolate, and they're getting better results. I've had a lot more people tell me that their doctors did a blood test and they told them that they had to stop taking the folic acid and start taking methylfolate, and they can't notice any difference. The methylfolate doesn't work for them any better than the folic acid, because that's going to be the situation for most people. That's what the double-blind, placebo-controlled clinical studies show. So folic acid works well for most people with the methylene tetrahydrofolate reductase deficiency. There may be a few that need methylfolate. But this is not the myth that you're being told. It's not everybody with a deficiency. It's not better for everybody out there. Folic acid works well. So we think about it. Here are the myths. Methylfolate is natural. Folic acid is not. That's false. Folic acid isn't found in nature. That's partly true, but irrelevant, because remember, we scavenge it as quickly as it's formed and convert it back to tetrahydrofolate. Methylfolate is better utilized than folic acid. That's completely false. If you have a mutation in the methylene tetrahydrofolate gene, folic acid isn't effective. That's false. Excess folic acid can cause cancer. That's false. Number 6, folic acid can mask B12 deficiency, while methylfolate does not. That's true, but it's easily correctable. You make sure that your supplement is not just folic acid, it's folic acid and B12, and I would recommend folic acid, B12, and B6 together. So if we think about the myths that are out there, the emperor has no clothes. You might remember that story. The emperor one day took it upon himself to go strolling in his kingdom without putting his clothes on. And his advisors didn't dare tell him. And the people, the adults lining the street didn't dare say anything. And finally one kid came up to him and said, "Why aren't you wearing any clothes?" So I want to be that kid that comes up and asks, why aren't they wearing any clothes? Why are these myths still perpetuated when they're not true? So, again, I told you I would sum it up and tell you what I told you. Most of what you've heard about methylfolate is myth, not fact. Folic acid and methylfolate have the same effects in the body. Folic acid has much better research in methylfolate. For most people out there, 99, maybe 99.9% of the people, folic acid works just as well as methylfolate, even in people with the methylene tetrahydrofolate reductase deficiency. And folic acid is less expensive than methylfolate. So why would you want to use methylfolate? By the way, the other one I didn't put in here, but we covered, methylfolate is no more natural than folic acid. In fact, it's made from folic acid in a series of chemical reactions. So, thank you for joining me. I hope this has been helpful.